So let's look at Vitali's covering lemma. Is the following statement that if you have a finite collection of open balls in Rd, say B1, B2 up to Bn, then there exists a disjoint subcollection. So the disjointness is important here. Disjoint subcollection Bik, k from 1 to small n of B, such that the measure of the union is bounded above by 3 to the power d times the sum of these balls from the disjoint subcollection. So the idea here is quite simple. It simply says that if you have two circles B1 and B2, then the second circle, so say B1 is larger than B2, B1 larger than B2, then if you take the circle or the ball of radius 3 times the radius of B1, so one here and one here, so 3 times the radius R, then this will envelop both B1 and B2. So in this case we only have two open balls B1 and B2, and the union of B1 and B2 can be enveloped by a ball of center, the same center as B1 and 3 times the radius, so that here you have M of B1 union B2 is less than or equal to the measure of the ball. So let me write this as B1 prime, which has radius 3r. So this is less than or equal to the measure of the ball B1 prime, and the measure of the ball B1 prime is precisely 3 square times the measure of B1. So this is in R2. In R2 we have this picture. So this is the Vitali's covering lemma is a generalization of this statement for any finite collection of open balls in Rd. So let's see a proof which is not constructive but rather more algorithmic. So step 1, choose the ball of maximal radius among this collection in B. So say BI1. So here note that if there are more than one ball, if there is more than one ball of the same maximal radius, then we can choose randomly from this subcollection, then choose randomly from the collection of subcollection of balls, of open balls in B with the largest maximal radius. So maximal radius here means the largest radius with the maximal radius. So if there are more than one, then we can just pick one and then we repeat this process for the next one in no particular order. And because there are finitely many, there are no issues with choices. So So the first step is to choose the ball of maximal radius in B, and say this is BI1. So step 2, delete all the balls, all the open balls in B which have a non-trivial intersection with BI1. So what are we doing here? So suppose we have many balls like this, something like this, and so if you choose the one with the maximal radius, this is this one, this is the one with the maximal radius, which is denoted BI1. And now we are going to delete all the open balls in V which have a non-trivial intersection with BI1. So all these little ones which are either inside or have a non-trivial intersection with them, with the BI1, are deleted. So these are all deleted from B, and now we are left with a sub-collection B prime in B, and then we are going to repeat the same process. Now as a remark, note that all the deleted balls in step 2 can be engulfed with the open ball centered at the center of BI1. So with the same center of BI1, say XI1, and radius 3 times the radius of BI1. So because if you, just as we saw before in this example, any two balls which intersect, if you take the larger sized ball and you take the ball of radius 3 times its radius, then it will engulf both these balls. So in fact, if you have any number of finite number of open balls, this can be done for the same argument applies. And so this, all these deleted balls, this one, this one, this one, and this one, they are engulfed by another big ball which has radius thrice the radius of B1. Okay, so if this is R, this is 3R, and you can engulf all these balls with the bigger ball. And now we are left with a sub-collection B prime for which we repeat. So we get another another ball of maximal radius BI2. Then we delete in the next step all the open balls intersecting BI2 and so on. And since there are only a finite number of balls, this repetition of step 1 and step 2 will terminate at finite time. So after at most n steps, after at most n repetitions of steps 1 and 2, we get a sub-collection B prime given by BI1, BI2 up to BIN, such that first is that this is a disjoint collection. B prime is a disjoint collection of open balls, in B, because we have deleted at each point all the balls intersecting BI1. So therefore, in particular, none of BI2 up to BIN intersect BI1, and similarly for the rest. So this is a disjoint collection of open balls in B. And secondly, we have that the measure of the union BI, I from 1 to n, this is less than or equal to 3 to the power d times, well, let me write this first. This is less than or equal to the union k equal to 1 to n, the ball with the same radius as BI1 but with 3 times BIK, but with 3 times the radius. So 3 BIK is the open ball with radius 3 times the radius of BIK and same center. And now again using the scaling property for the measures of balls, this is less than or equal to the sum bounded above by the sum of the measures of 3 BIK, and this is precisely 3 to the power d, 3 to the power d measure of BIK, k equal to 1 to n, and this is what we wanted because you can take the 3 to the power d outside. So we get a disjoint collection of open balls in B which satisfies this inequality that we wanted. So this is the proof of Vitali's covering lemma, and now let us see how the Vitali's covering lemma will help us in proving the Hardy-Littlewood maximal inequality in RD. So we return to the proof of part 3, which is the Hardy-Littlewood maximal inequality. So you have to show that for alpha positive, the set A alpha defined as the set of all points x such that MF of x is greater than alpha satisfies this bound, which is the measure of A alpha is less than or equal to 3 to the power d over alpha with times the L1 norm of f. So remember that f that we started with was an L1 absolutely integrable function. So let for each x in A alpha Bx B, or rather Bx Rx be an open ball of radius Rx positive such that we have 1 over measure of Bx Rx integral over Bx Rx mod f dm is greater than alpha, because if x is in A alpha, you can always find such a radius Rx. And now this is a collection of open balls covering A alpha. So this implies that A alpha is equal to x in A alpha Bx Rx is covered by these open balls. So now if we take, so I am going to use we shall use inner regularity for the set A alpha, so which is a Lebesgue measurable set. In particular, we showed that this is an open set, so in particular it is Lebesgue measurable, and so inner regularity holds. And so we will show that for any compact K inside A alpha, we have the required bound, which is 3 to the power d over alpha norm of L1, and by inner regularity this will follow that this would imply that measure of A alpha itself is less than or equal to 3 to the power d over alpha L1 norm of F, by taking the supremum on the left hand side over all compacts inside A alpha. So let K is be a compact subset of A alpha, then K is covered again by the union of all these balls BXRX, and by compactness there exists a finite collection let's say x1, x2, so these are the centers of these balls, xn. Let me write capital N here, such that K is covered by the union I from 1 to capital N B xi rxi. So this is now a finite collection of balls. So now we have measure of K is less than or equal to the sum, or rather the measure of the union I equal to 1 to n bxi rxi. Now we are going to apply the Vitali covering lemma to the collection B given by these sets Bx1 Rx1, Bx2 Rx2, and so on, Bxn Rxn. So then we can extract, this implies that there exists a subcollection, a disjoint subcollection, B prime of B, such that the measure of the union I equal to 1 to n bxi rxi is less than or equal to 3 to the power d sum over I equal to k equal to 1 to small n b xik rxik, or let's just say rik, right. So this was the statement of Vitali's covering lemma, which gave you a bound of the measure of the union of finitely many open balls by the sum. So let me write this in a new page. So this is wrong. Such that we have the measure of the union I equal to 1 to capital N bxi rxi. So let me just write this ri for short. This is less than or equal to 3 to the power d sum k equal to 1 to n b xik rik, where B prime, this subcollection B prime, is this collection bi1, bi2, or rather so each bik is bxi1 ri1 and so on bin. So we now can estimate this measure of the compact set by the Vitali covering lemma here as 3 to the power d I equal to 1 to n measure of b xi k, this is k, ri k. And now we will try to conclude. So note that for each k from 1 to small n, we have 1 over measure of b xi1 I k r I k integral over b I xi k r I k mod f dm is greater than alpha, because this was our choice of the open balls for which this held, this inequality held. So in particular for this subcollection also this will hold, and so this implies that the measure of b xi k r I k is less than 1 over alpha integral b xi k r I k mod f dm. And so we can use this here. Let's say this is 3, this is 2, and so we can plug in the values from 3 in 2. So we get, so from 2 and 3 we get that the measure of k, which was bounded above by this sum, first of all it was bounded above by the measure of the finite union of balls I equal to 1 to n b x I r I, so this was rxi, and this was bounded above by the Vitali covering lemma by a subcollection equal to 1 to n measure of b xi k r I k. And now from the third, so this is from the Vitali's covering lemma, from Vitali's covering lemma, and now from the third inequality we get that this is less than or equal to 3 to the power d sum k equal to 1 to n 1 over alpha times integral over b xi k r I k mod f dm, and this is equal to 3 to the power d over alpha integral of the union of all these b xi k r I k k from 1 to n mod f dm, since these are disjoint. So this was from the Vitali's covering lemma, gave us a disjoint subcollection. So this is because since b xi k r I k, these balls are all disjoint. And now this is less than or equal to 3 to the power d over alpha over the integral over all of r d mod f dm, and this is nothing but the L1 norm of f. So this is what we wanted to prove, that any compact set K satisfies this inequality. So K was a subset of A alpha, and now by inner regularity we get the result. So this completes the proof of Hardy-Littlewood maximal inequality in RD, and now we would like to go back to our proof for the Lebesgue differentiation theorem, which we stated only for the dimension 1, and what we wanted there was this bound on this maximal function, which was here. Yeah, so we wanted a bound on this maximal function, or rather we wanted a bound on the measure of the set where the maximal function is greater than alpha, and our maximal function was slightly different in the one dimensional case because it's only from one sided. So it's only for positive values of h, so it's what's called a one sided. This is a one sided Hardy-Littlewood maximal inequality. But of course, if you have the two sided Hardy-Littlewood maximal inequality, which contains an interval of radius let's say 2h with the center x, then the one sided Hardy-Littlewood inequality will follow, because if you define m tilde f, so remember that mf is this guy here, and now m tilde f, if you define it as the supremum, so this is at x, supremum over h greater than 0, 1 over h integral x minus h by 2 x plus h by 2, or rather let me just take here 2h and take x minus h and x plus h, and then you take the modulus of ft and integrate it over this interval. So our Euclidean balls of radius r are now replaced by these kinds of intervals. You can take open if you want, it doesn't matter here. And now we have this is the measure of this interval, and we have proved the maximal inequality for this m tilde rather than m, because we have used the measures of balls centered at x and with radius r. So one can now show that we can deduce our result for m from our result of m tilde, because this is always greater than or equal to mfx, because if you restrict this integral on this interval x to x plus h, then the integral will be dominated by this integral. This integral will be dominated by the integral in m tilde, and we will have that f alpha is a subset of f tilde alpha, where f tilde alpha is defined using m tilde rather than m, and so the measure of f alpha is less than or equal to measure of f tilde alpha, and for f tilde alpha we have proved the Hardy-Littlewood maximal inequality. So this concludes our proof of Lebesgue differentiation theorem in R, and in fact, since we have proved Hardy-Littlewood's maximal inequality in RD, and we have also shown this Vitalis covering lemma in RD, so in fact the Lebesgue differentiation theorem can now be easily proved for RD. So the statement of Lebesgue differentiation theorem in RD is the following, that if you take an L1 function in RD, and if you take the limit as r goes to 0 plus 1 over measure of bxr integral of f dm over bxr, this is equal to fx for x almost everywhere in RD. So here as an exercise, I will leave it to you as an exercise to check that the proof for R goes through in this case as well. So in particular, you have to show that the limit as r goes to 0 plus 1 over the measure of bxr integral over bxr g dm is equal to gx for any continuous compactly supported G in RD. So this is the first fundamental theorem of calculus for RD, fundamental theorem, and I leave it to an exercise to prove this result simply by using the continuity of G as we have done for the one-dimensional case. So this completes the proof of Lebesgue's differentiation theorem in RD. Just by repeating all the steps by using the Hardy-Littlewood maximal inequality in RD, and then using the Markov's inequality as well as the Hardy-Littlewood inequality to prove that the measure of the sets for which this is not true is equal to 0 by taking the limb soup and the same way that we did for R. So this is one of the main differentiation theorems that we wanted to see, and in the next lecture we will move to a related topic.